Hello students, and welcome to the first video of the last topic. We are dealing with non-linear functions in this topic, and that just means essentially that the graphs are not straight lines, there's some sort of curve. We're going to start with the quadratic function. Quadratic means that our equation, our expression, has an x squared term in it, and nothing more complicated than that. No higher power than an x squared, so no x cubes or fourths or anything like that, and no x's in the denominators or anything else that might be vaguely complicated. Just something in the form y equals, in fact we're going to keep them easy here, y equals some lot of x squared plus some other number. Right. It's going to make a bit more sense once we see some of those. The shape of that graph is called a parabola, and that's got some useful physical properties. Let's have a look at a few graphs so we get an idea of what they look like. So y equals x squared is the most basic and straightforward form that we're going to see. And its graph looks a bit like this. You can see it curves like this. We call that concave up because the ends are pointing up. These should by rights have little arrows on them and little x and y label here on these axes. But you can see the sides aren't straight. It curves all the way. It gets steeper further away from the center. That center point there is called the vertex. And you can see it's symmetrical. It has an axis of symmetry here. It's the same on one side as the other. It points upwards. It's concave up. This one here is negative x squared. And so that does sort of the opposite. At the ends of that point downwards. It's concave down. And we can sort of remember this, that if I put little eyes on here, it looks like a smiley face. This looks like a frown, right? Because this one is positive and this one is negative. Okay, negative x squared means the ends point down. Yeah, concave up, concave down. Axis of symmetry, vertex. So y equals x squared concave up, and y equals negative x squared is concave down. Let's have a look at a couple of others. What about these two? Y equals x squared plus 3, or x squared minus 2. What does this constant on the end do to our function? Well, here's the graph of y equals x squared plus 3. You can see that's the parabola we had before. Still has that same axis of symmetry, but the vertex, instead of being at the origin, has now been lifted up to 3. So the coordinates of that vertex are 0. Right? We start at the origin, we go across 0, and up 3. 3. Not a coincidence. Now the graph over here, it's still concave up because it's a positive x squared, right? Concave up. But instead of being lifted up 3, it's been pushed down 2. Oh, yeah, so we see that happening. That's what that constant on the end does. Lifts it up or down, right? Moves the graph up c units when it's written like that. Rightio, some more here. What if it was 2x squared or half x squared? How would that look? Well, I suppose, let's have a look at this. Can we determine the difference there? Notice it still goes through the origin because it doesn't have a constant on the end. It's a multiple of the original. Can be a bit hard on its own to see how that's different to the other parabolas we've been looking at. But we'll notice the difference when we look at half x squared. So what's happening here is that the sides of this one are steeper. It goes up faster. Right? The 2 makes the sides of that graph go up faster, whereas the half make them go up more slowly. Okay, so if you like, the sides are steeper, or we might say that this sort of is skinnier and this one is wider. Right here. So what happens if I put a number more than 1 out the front there? Then the sides get steeper, and a small number makes the sides less steep, makes the whole graph appear wider. So we mentioned the vertex, right? That's where it stops going up and starts going down, or the reverse. Okay. But it's where the axis of symmetry meets the parabola. We'll have a minimum or a maximum. That should make sense. Right. Let's see here. Sometimes we'll draw these with a table of values, and I think I've got an example of that here. So here's a graph. What's it going to look like? It's got a negative before the x squared. So that means it's going to be concave down. and its y-intercept, the vertex, will be at 4. But I'm just going to draw up a table of values. It hasn't told us what values of x to use, but I'm going to go from -3 to 3. I think that covers us reasonably well. So we've got that, and now we substitute in, right, these numbers one at a time. I've started here at the right. So 3 squared, right, 3 squared is 9, 3 lots of 9 is 27, 4 minus 27 is -23. Repeating that with 2, 2 squared is 4, 3 lots of 4 is 12, 4 minus 12 is -8. And we'll repeat that. Now something that we're going to find here, there's a 1 has appeared for the second time. There's a -8 has appeared again, and this one here, -23. Remember that these things are symmetrical, and we can use that to our advantage sometimes. So now we're going to plot these points. So my x and y axis here with a nice neat scale. I'm going to put these points in one at a time. So -3, -23, across to -3, down to -23. There's my first point. Second point, -2, -8. -2, -8. There's my second point. Third, -1 and 1 is up there. 0 and 4. And you can see I've reached the vertex. It's gone up and it's coming back down with a certain amount of symmetry. Am I going to get in the road? No, that's okay. So I've plotted enough points there to draw a nice neat curve through it, and there's my nice neat curve, right? Lovely neat parabola. Went through all of those points. So we have drawn a table of values. We've sketched the curve. Where's the vertex? It is at 0, 4. Here we go. Okay, another example. Graph this one and find its vertex. A half x squared, it's concave up because it's a positive x squared. And the vertex is going to be at, well, I can see here at -1, 0, -1, but the sides will be fairly less steep, flattish, if you like. So once again, let's draw up a table of values, substitute in to fill that out. So -3 squared is +9. Half of 9 is 4.5. 4.5 minus 1 is 3.5. We'll keep going. We'll fill out that table of values. And again, we're going to see, well, here's my symmetry occurring now. So there's my -half, -half. This one's going to be a 1, and this one a 3.5. Right, you can see the symmetry in the table of values. We're going to see that, of course, on the graph as well. So here's my axes again. Let's plot these points. -3, 3.5. Right, there's -3, 3.5. Then I want to go -2 and 1. Then I want to go -1 and -0.5. So it should be here. It's working out fairly well. And we'll put those other points there, place them on one at a time. We can see the symmetry in it. We'll draw a nice smooth curve through them. There we go. And we identify the vertex at 0, -1. So far, so good. Right, keep moving along. That's the end. It's the end of our first exercise. So let's just go back over some of the things we learnt there. Quadratic functions have an x squared term, and not much else. Shape of the graph is called a parabola. Can be concave up or concave down. Positive x squared is concave up, negative x squared is concave down. These parabolas have an axis of symmetry, and where the axis of symmetry meets with or intersects the parabola, that's where we have our vertex. Right, let's get out of the road there a little. Okay, that's it for quadratic functions. We're going to look at some applications of those with maximum and minimum problems in the next video. See you then.